Hello. So the first two assumptions for least squares methods was the first conditional mean zero assumption and second IID assumption. And the third assumption we are going to discuss in this video is about outliers. Simply speaking, your data cannot have too many outliers. So the outliers should be rare enough. Otherwise you cannot guarantee that your analysis results is true. So your analysis could be wrong, can be wrong due to the presence of outliers. So you know what the outlier is. Outlier is an extreme value. Like it could be about X or it could be at Y. So in our analysis between test scores and student to teacher ratio, if you have outliers in either of them or both, then you are in trouble. Both of those variables should be reasonably refined, so without outliers. And outliers cause a lot of problem, as you will see in the next slide. And then however, so it's not easy to define like mathematically what is an outlier. So how extreme is an extreme value? That's a little bit subtle, and there is no crystal clear rule, but the textbook uses this condition. So I'm not going to discuss what this means. So fourth order moment is finite. So fourth order moment usually talks about the thickness of the tail, how thick the tail is. So the tail should be thin enough. If it's too thick, then so your distribution will go down to zero as you go outside, and it should be coming down to zero quickly enough without long tail. So anyhow, so mathematically it's hard to verify and hard to check it in the data, and usually it's trivial. But what is generally recommended is to look at the data, try a graph, or at least calculate the maximum and minimum values of all the variables, and see if there is any strange pattern. So just drawing a graph is enough. Scatter plot or graph would help a lot. So almost always that's the first step in your data analysis. And almost always whenever you have some kind of strange weird results, or you got some errors in your algorithm, then in most of the cases it's because of some kind of outliers or missing values. So both are problems. What is it? So like for example, if you have a graph scatter plot, think about this guy, obvious outlier. So you don't need any mathematics. It's obvious outlier. I believe it must be a typo of 170. So 170 was mistyped as 1700. So something is wrong. Then the problem here is, so without this guy, you are going to have more flat regression line, estimated line. But when you add just one outlier, your regression results changes like this. And so even though it's not clear, but as you see, excluding this outlier implies a downward sloping regression line. So the true line, if this was an error, the true regression line was negative, downward sloping. But because of this error, it suddenly becomes very much positive, strongly positive, just because of one observation in the data. So as I said, it happens, maybe I guess, so it was mistyped, like put one more zero is kind of somehow one more zero is added, or some number has been mistakenly typed, or there could be many different reasons. So for example, when you analyze the stock market, if you include Apple or Tesla, somehow it could be misleading. They are so outliers. So most of the firms are not like Apple or Tesla in their stock returns. So handling those kind of things is very important, and like when you have a graph like this, and if you observe that there is an outlier, then I recommend you to see how much it changes without this observation. Assuming that it is an error, then if you exclude this, and if the result changes a lot like this, then you have to think about this more seriously. If the result does not change, then that's not a problem. So if the result with or including or excluding the outlier are similar, then what's the problem? There is no problem. So there's more practical way to check if there is an outlier or not is to compare how sensitive your result is to whether you include or exclude the outlier. That's what I can tell you here. So we have considered 3 assumptions, and from here the next topic we are going to study is the sampling distribution. So before talking about the sampling distribution for the regression model, I am going to remind you of what the sampling distribution means in more simpler, easier setup. So I think the good starting point is this. Imagine, so basically no matter what data you have, it is generated from some kind of random experiment, and all the data are results of repeated experiments. That's the very basic concept, the fundamental idea of statistics. And after repetitions of an experiment, you observe many outcomes. So they may be different. The outcomes will be different from one experiment to another. So then if you combine or collect all the outcomes and make a graph, then you are going to see a histogram or a scatter plot, a graph. So then that's your distribution. That's the distribution from that random experiment, right? And conceptually, if you can repeat the experiment for an infinite number of times, you can observe the true distribution, right? The true distribution of the outcome is available if you could repeat the experiment for an infinite number of times. Of course, it's not possible in the reality, so it's just purely conceptual, mathematically hypothetical object. We are going to do something similar here. Now, the difference here is that our experiment is a little bit different. So the underlying original experiment is to draw one school district and observe the test score and student-teacher ratio. So one school district is drawn from one experiment, and you observe a pair of outcomes. That is the underlying original distribution, original experiment, but we will change our framework, and we will take one step back and see what's going on even in a bigger picture. So the experiment is to draw a random sample of school districts. For example, in our data, we have 420 school districts observed. So randomly choosing 420 school districts is one outcome. One experiment, excuse me. So one experiment generates 420 observations at the same time, and the final outcome is the OLS estimator. So from the 420 observations, you can calculate the regression coefficients, and that is the outcome from one experiment. So one experiment generates 420 observations, but in the end, it also results in one OLS estimate, right? So one experiment, one OLS estimate, right? So then, if you repeat this now, if you can repeat that experiment, repeating the experiment means that I have 420 observations now, and after calculating the OLS estimator, I will throw them away, throw away the observations, and resample another set of 420 observations. Redraw 120 observations and recalculate the OLS estimator from the new sample. Then you will get a different value from the first outcome. So by that way, that's the second experiment, and you can repeat this again and again. Conceptually, it's usually not possible, but just it's a like kind of mathematical experiment, mind experiment. So, and when you can repeat it like for an unlimited times, then in the end you are going to see a distribution of the OLS estimator, right? So each experiment generates one OLS estimator. So in the end, in the limit, you are going to have the true distribution of the OLS estimate. We call that the sampling distribution of beta hat, sampling distribution of the estimator. So this is, so compare the framework. So the first two lines, it's too trivial to you. If you repeat the experiment, you see some kind of distribution. So now then, into this framework, I'm going to put a new experiment, which is a little bit, which is weird and which is not possible, but there is no problem imagining something like this, right? And you know already something about already a famous sampling distribution for the sample mean. This is the most famous sampling distribution theory. The sample mean x bar, which is defined in this way, summation of xi divided by n, by the central limit theorem is approximately normal distribution. So this means the x bar minus sample mean minus the population mean, and if you multiply square root n, then as n goes to infinity, its distribution converges in distribution to a normal distribution with the underlying variance of x. So simply speaking, when n is large enough, then this distribution can be approximated to a normal distribution like this. Or already that is done here. So this t statistic, this is the t statistic, something like t statistic, and that is approximately standard normal distribution when sample size is large enough. It is not exact distribution, but it is an approximation to a normal distribution by the central limit theorem, but it is still, it's very powerful. And if you have taken, so when I teach 320 economic statistics, everything is based on this. All the theory all the theories rely on this theory, this approximation, normal distribution. So it implied a lot of things. First, it implies the mean is 0, approximately 0. So that means unbiased. So x bar is expectedly mu. So x bar is an unbiased estimator for mu. And standard error can be calculated from this. So we know so because of the multiplied coefficient square root n, so the denominator must have square root n. And later on, we are going to use the normal distribution to calculate the confidence interval and the p-value. I have done that in economic statistics course. So we are going to study something similar in the regression model. There will be many mathematics, but I'm going to skip most of them. So don't worry about the mathematical equations. Just get the idea, look at see the intuition, and see you in the next video.